Right. When I had to write the abstract for this talk, I thought to get everybody's attention, I'd talk a little bit in the abstract about how we were misusing the fossil fuels that we've been left by history. So there was something called the Carboniferous Period. It ended about 300 million years ago. It wasn't all that long. It was only 60 million years long. And we have been digging up systematically in the last 100 years the fossil fuels that were left during that period. And we're using it, and I put in this might be a bit of an exaggeration, but I put it in the thing that we're using it at 1 million years to 1 year. Now, if you do the sums, maybe I'm a little bit out. Maybe it's only like 100,000 years to 1 year, but still it's kind of scary, and it's a lot like using your bank account, the money that's in your bank account, as if it's your income, which of course is the UK government's new plan for pensions. Not a good plan, and really not where I'm coming from. I think we've got to change our behavior to the point where we're using the sun's energy in the year that it's provided to us. And that we've got a long way to go before we can do that. Now, when I got off the train in 1978, the world had 2 oil shocks. And this had so modified that the world that even the big 3 car makers in North America had completely revised their range of cars. That's how seriously they were taking this. And then in the 1980s, it all disappeared, and we could all have big cars again, and everybody kind of forgot that we were living on our capital. And that continued for a while, and it comes up and down. It's a kind of cyclical wave as we sort of appreciate that maybe fossil fuels aren't forever. But more recently, there's been a little more focus on this issue, not necessarily because we're running out of fossil fuels, but because if we burn all the fossil fuels we know about, we're in deep doo-doo. And the deep doo-doo is a result of the carbon dioxide that burning fossil fuels creates. And the really scary thing, and this book, I'm going to give you 3 lots of homework tonight, by the way. This is the first one. This book tells us effectively that if we burn more than 1/3 of the fuel that's sitting under the ground that's already been monetized by the big energy companies, then we're going to go over 2 degrees C. And that's really quite scary because somebody's already put a value on the stuff that got under the ground, and we know if they extract that value, then it's going to be very difficult for the rest of us. And so something needs to be done. I'm not going to talk about the whole problem tonight. I'm only going to talk about the electrical grid. This is where I have to get technical. I have to make something happen here. Is that working? Yeah? Yeah, okay. The electrical grid is a phenomenal thing, and there's a page on the web called Grid Watch. Are we not working? No, we are working. Oh, you're putting lights down. Excellent. There's a page on the grid called Grid Watch, and it's like having a dashboard to control the universe. It's fantastic. So I want you to I'll just explain this for a moment. I don't think I have a laser pointer here, but I do. Oh, it's there. Right, okay. Along the top, I've got big gauges. These 4 are telling me how much energy or how much power is coming out of 4 major sources. Coal, nuclear, gas turbines, and wind. And those 4, by and large, plus the little minor sources that we see in the little gauges, they go to equal this, which is the demand. And the interesting thing about the electrical grid is there is no storage. Everything has to happen in real time. So the demand has to exactly equal what is supplied. And if we look at what's happening during a day, we see it sort of rolling along here. When it's nighttime, the demand is lower, and then it ramps up in the morning, and then during the day it's fairly constant until we get to sort of tea time, and then it has a hump. And these different forms of generation must come together to provide exactly what we need in the second that we need it. There's no elasticity. So in the grid going forward, we're going to have to maintain this because this is how AC electricity works. But we've got some interesting problems on the horizon, particularly if we want to decarbonize our grid. Now, just by way of filling the picture a little bit, when we have the way the electricity works at the moment is that there's a kind of continuous auction that goes going forward. And the time is divided up into half-hour slots, and different generators are bidding to sell electricity into those half-hour slots. And this is a result of maybe a couple of weeks ago, just over a 24-hour period, how the price of electricity has varied through that maybe 24 or 48 different little time steps. And what's interesting is that from the lowest, which is around just under 20 pounds a megawatt hour, to the highest, there's almost a factor of 3. So the price is actually varying quite a lot. And it will vary when there's when we get to sort of desperate measures, and having things that vary in terms of the generation and the demand may increase the number of desperate measures that occur. Now, my argument is that we're going to have a lot more of these, because in decarbonizing the grid, we're going to have a lot of solar and wind and other forms of renewables, and we don't get to choose when to turn those on and off. They essentially react to the environment that they're in. So these are solar panels. You've seen them before. There's the kind that you mount on the roof, the kind you put in the field, and then there's this kind that you can sort of steer towards the sun. And you'll notice that all these are kind of made of a kind of blue-black material, which is a silicon material. It's just like making it's made just like integrated circuits or microprocessors, and it's very, very energy intensive to make. The result being that you make something like this, you put it on your roof, and you spend the next 4 to 6 years, if you're in Scotland, earning the energy back that it took to make the panel. So you're actually, although you go and look at the meter and you think this is good, in fact, somewhere in the world, there was an energy hole that was made that will endure for 4 to 6 years until you get to parity. And then you're in profit. But that's quite a long time. That concept, by the way, is called embodied energy, the energy that's embodied in the making of the device. And for any device to be useful to us, we've got to make sure that the embodied energy isn't too high. So let's have a little quiz. So I'm going to do a page down. So I've got a little balance here. We're going to talk about embodied energy for different forms of generation. So I need some audience participation. I'm going to talk first about coal. If I build a coal plant, how long does it take? How long do I have to operate it before I've paid off in terms of energy that's generated by the coal plant? How long do I have to operate it before I've bought the energy for the concrete and the steel and everything else that goes in the coal plant? David, you look like you have an answer. Don't know. Anybody got an answer?
10 years.
2.5. 2.5 years. So the first 2.5 years that plant operates, it's just getting back out of the hole. Let's do the same. Let's do the same thing for nuclear. Any guesses on nuclear? How long it takes to? 7 years. I think somebody's been priming you. It's actually half that. It's 3.5 years. So longer than coal, but maybe that the embodied energy in this case doesn't include the cleanup costs, which I'm sure it won't include. Now, here's the trick question: how long does it take wind to overcome its embodied energy? 6 months, I hear. 2 years. 10 years. Well, there's a lot of misinformation about wind because there are a lot of people who love to hate it. But actually, there's some fairly good answers. If by the time it's about 6 months for the actual turbine, but by the time you build the track and put in the cables and so on, it's around 1 year. So it's 2.5 times better than coal, 3.5 times better than nuclear. And there's a really important feature in wind and solar PV. To get to the equality or the parity point, I didn't have to put any more energy into the wind turbine because the wind was doing that for me, whereas I've still got to buy the fuel for the coal plant and the nuclear plant. I just put that in to dispel some misinformation and also to get across the idea of embodied energy, which is quite important. Now, I started working as an engineer 37 years ago, 1978, and that date will come up again and again, but I found this graph which is showing the decrease in price of solar PV during my working life. and it's come down by a factor of 200. That's quite interesting, 200. That's for the very common garden silicon type of panel. But it's still not cheap enough. It's got to be cheaper if it's going to be as pervasive as we need it. So this is, I'm afraid, a very complicated looking thing. We're really interested in this pink patch here. The blue thing is basically the efficiency of silicon type solar PV as it developed through the ages back from 1977. And you can see there's a sort of slow, monotonous climb, and it's sort of peaking out about 25%, turning sun energy into electrical energy. There's some really expensive stuff up here using very rare materials, but we're not interested in that. What we're really interested in this, and the reason I'm showing you this, is that just recently, so like since 2010, there's a whole bunch of new things creeping up from the bottom here. Now what this doesn't show you is how expensive these materials are, but the important thing is that the ones here are so cheap that they're almost free. And that's going to make a really, really big difference to how energy is generated, how electricity is generated in our grid, because if I'm able to make free solar PV that has very low embodied energy, how am I going to get the money together to buy, to build big generating plants anymore? It's going to be an interesting question. So, given that solar PV has this immense potential, I went, and this is the second piece of homework, I went and looked at this book written by my good friend David Mackay. A few of you in the audience will know him. And he did this fantastic thing for us. He actually took our use of energy in the 20th and 21st century and broke it down into all of its constituent parts and put it all in the same units, and then he went and looked to see where we could get it from in a sustainable way. And I recommend this book. It's written in fairly accessible language. So if you go and look in it and look up about the solar PV, you'll find that if you had solar panels that were working at about 15% efficiency, and if you covered all of the 1% of the UK's area, like all the roofs and the walls of buildings that you might build, with panels that had almost free solar PV material on, you could generate just about the average requirement of the UK, which is around 35 gigawatts. So that's interesting. We can get all the electricity we need just by putting new roofing materials on our houses and maybe building a few of these things in the field. Problem solved. Except there's a bit of an issue with the word average. So this is a time history of what happens in a solar plant. I've pinched this off somewhere on the internet, and it shows you the output of some solar panels. I'm not sure where, but it's sufficient for my purposes. So the first thing you'll notice is that around about dawn, the panel starts to generate, and it generates in a kind of hump pattern. So around midday, it's at a maximum about 4 megawatts, this particular panel, and by dusk, it's off again. So you get this sort of general feeling. But you've got all these funny little sawtooths in the pattern, and that's the sun coming across the sky. Sorry, not the sun, the clouds coming in front of the sun. And when the clouds obscure the sun, solar PV materials are incredibly sensitive, which is why recently in Germany, because they've got an awful lot of solar PV, they were very concerned about that eclipse, if you remember. Because whereas a cloud might be in one place or another, the eclipse was everywhere at the same time. So, but this does show us how important it is to have direct and intense sunlight on the solar PV panel to make it work. The final point is that this only really shows us the daylight hours. There's a whole bunch of non-daylight hours where we get nothing. So the word average is really important, because although we could make our average requirement with solar PV, we're not going to be able to meet our instantaneous requirements, and we've already seen that the grid works in real time and instantly. So what can we do about that? Well, let's look at how electricity is generated right now. And up at the top there, you've already seen that. That was on the Grid Watch panel. I stole that away. And you'll see that this bigger rectangle is in fact that same thing but blown up. but this time it's blown up to show the different forms of generation that are used to create that total amount of electricity. The orange one at the bottom is nuclear. So you see you've got this sort of almost continuous output of nuclear plants, and the top one, the gray one, is coal, and it's very continuous. So although the demand is changing quite radically, these two constituents are actually remaining very constant. And as a result, they get called base load. And when you hear people being very rude about wind, they say, we want base load, because they think base load is something really wonderful. But I think in the world to come, the intransigence of this kind of generation is going to become a real problem. I can probably see a nuclear expert, Keith, right back there, wiggling in his chair as I say this. But this is going to be a bit of an issue, because you can see that the demand is changing greatly, but these two providers are not. They're actually fairly constant. So what are we going to do about that? Well, let's see what we do at the moment. We supply that blue band at the top that's actually meeting most of the ramping demand with something called a combined cycle gas turbine, which is that kind of plant there. And that currently is the way that we keep the lights on, because it's able to ramp up and down, and that's currently effectively the major tool for accommodating the variations in wind and solar PV and all the other generators, minor generators that are on the network. There is another thing that I want to just draw your attention to. It's so subtle that it's very hard to see, but there's actually two very narrow little bands, one there, blue, and a little green one there. And those are forms of hydro. And if you look carefully, you can see that the hydro is really only coming on when the demand is high. And that's because they are also able to ramp up and down. And we'll talk about that a little more later. So if we end up in a world where there's a lot of the electricity is being supplied when the sun and the wind want to supply it, and we don't have any non-carbon version or non-carbon generation that's able to ramp up and down, what are we going to do? Well, one of the things that's talked about of late is the Internet of Things, and people sort of think about it being a convenient way to turn on the kettle before they get home or whatever. But in fact, it gives us a tremendous connectivity to a lot of devices that consume power. And it means that, for example, you could have your own little private auction with your washing machine and tell it to turn on when the electricity price drops below a certain threshold or whatever. And so suddenly we've got the prospect of varying demand. And this could be really quite exciting, because there's quite a lot of things that we use electricity for which we're not particularly, there's no particular schedule that we have to adhere to. We wouldn't like it if the television was turned off while we were watching it, or if the lights were dimmed in our house. But there's a lot of things like heating water or washing clothes that we probably could manage to have some latitude with. Now the Internet of Things is what's coming, but I want to show you what happened, just because it's rather funny. And this is a paper that Stephen, sitting in the audience, wrote in 1977 when he proposed that we could vary the demand by putting microprocessors into the individual things that were in people's houses and wherever else, and that those things would sense the grid falling down in frequency and selectively turn themselves off. The result from the very centralized electricity generating board was this comment at the bottom: they must be smoking strong stuff up there in Edinburgh, which was interesting and revealing, because I think demand side management is going to be one of the big factors that allows us to keep the grid working in the future. And it's not just domestic stuff. There are a lot of big industrial processes, like, for example, compressing industrial gases to either liquefy them or separate them. There's smelting of aluminium and other foundry type operations. There's making of industrial chemicals like ammonia for fertilizer. There's enormous numbers of these things, and a lot of them already have arrangements with the grid operators so that they can drop out. Things like industrial refrigeration like massive warehouses supplying cold space for food, these things can turn off for half an hour and nobody knows. And the interesting thing about demand management is that it's 100% efficient. So if I turn off my industrial refrigeration unit for half an hour, it probably won't notice. And when I turn it on to catch up when the grid's recovered, then in fact I'll have essentially just moved that electrical generation an hour or so ahead in time. And that's 100% efficient, and it costs me nothing to do that. So that's a neat, interesting kind of ramping storage that we will certainly be taking advantage of as the world develops. Now, I mentioned those two little slivers, and they're not very big in terms of the magnitude in the UK. They're very big in Norway and also Canada. But hydro is one technology which can be used to create buffering and variable levels of energy storage on the grid. But I think it's worth at least reminding ourselves how hydro works. There's actually three kinds of hydro, and it's worth just exploring this for a second. The first kind is what you put in a river, and that just is operating on what's called a must-take basis. The water comes, you can't hold it back, there's nowhere for it to be held back, and that just gives you whatever, just like the wind or the sun, it gives you whatever it's going to give. But then you move upwards, and now there's a very common sight in the highlands, this sort of dam, and the water can be held back behind the dam, and we can actually selectively use that water when the grid needs it. And we saw some evidence of that in that usage profile that I showed you earlier. And that's great, except that the water comes out of that system and it goes down into a river somewhere and probably out to sea, never to be used again. So that allows us to sort of schedule that output from that. But then there's a third type, which is called pumped storage. So I've got that dam high up, I've got a pipe and a turbine going down to a lower place. If I have another reservoir at the lower place where I can capture the water that's come from the upper reservoir, and if I make the electric and pumping machinery reversible, then I can take the water in the lower reservoir and I can push it back up the hill when I've got a lot of electricity, and I can store that energy in gravity by moving the water up the hill. And we have a lot of pumped storage in Scotland and in the UK, or at least we think we do, but we're going to need a lot more. We've got 3 gigawatts at the moment. We've got 0.6 gigawatts in plan, so we'll have roughly 10% of our generating capacity will be available as storage when that project is finished. But we're going to need an awful lot more. Incidentally, there's about 120 gigawatts worldwide, and for storing energy, this is 99.5% of the world capacity of energy storage. It's almost nothing else. People are building batteries and stuff, but this is the big thing. And pumped storage really, because it is the dominant player, it provides all the metrics. So its efficiency is important. It's about 75% efficiency round trip. So every unit of electricity you put into pumped storage, you only get 3/4 of that unit back again. So you've got to figure out how to value the storage to make up that difference in price. But there's a few other things about storage. At the moment, the pumped storage is you see it sort of at the edges of the fringes of our country. There's 2 stations, about to be 3 in Scotland, and 2 quite big, or 1 very big one, and 1 moderate-sized one in Wales. They're at the fringes of the country because they have to be in places where we have this particular geography and where we have no people. And of course that makes another problem, because then we've got to get electricity to it and from it, and that means quite long transmission lines. And it does mean also that the possibilities of extending this and making a lot more is limited. And as I said a minute ago, we probably need 10 times as much in order to make a decarbonized grid work. So, the challenge. We've got, and I'm summing up here, we've got looming on the horizon a lot more wind, a lot more solar PV, and the solar PV is going to be almost free, so it's going to be very hard not to install it. And we've got all these loads that we make, and machinery and industry makes, and we've got to figure out how to buffer the 2 sides so that it works in real time. And that's our challenge. We've got some tools already in our box in terms of pumped storage, but we can see that there's limitations, and maybe we've got to develop some new tools. In fact, in the lead up to this, various of my friends sort of said, well, so you're chair of energy storage, what are you going to do about it? And that was like a major weight to put on your shoulders, by the way. Anyway, that green box is why I'm talking to you tonight, and you've now had the preamble, so now we're going to get into the meat. Down. So when you look at storing energy, there's actually incredible range of things that you can do. And each of these colors represents a different field of endeavor. And of course, I'm not an expert in very many of them. I'm sort of specialized in the sort of blue and green one off on the top right. The other ones I know very little about. But at some point, all of these are competitors on this new stage for how we're going to make the grid work. So what I thought we'd do tonight is just look at these competitors and see where the competition is actually going to happen, and see if we can unmask the pretenders and put them in the dustbin so we don't have to work too hard. And as part of that, one of my friends introduced me to a chap in America, MIT professor, and I don't usually like having video clips going. He's actually working on a battery, so you hear the word battery, but forget the word battery. Just listen to what else he's going to say, because it's quite relevant to this discussion in terms of us unmasking the pretenders.
This battery needs to be made out of earth-abundant elements. I say if you want to make something dirt cheap, make it out of dirt. Preferably dirt that's locally sourced.
So this guy, Donald Sadoway, is a fantastically popular academic in MIT. His lectures, they usually have 20 people per lecture. He filled a lecture hall of 600 routinely till they actually had to put him on video, and then Bill Gates started watching his videos. He's quite a bright and a chap, and he's got a very good idea, and maybe his idea is the one that's going to win. In any case, this is another slide I've stolen from him, and the important thing about this, and again, it's a rather complicated thing to absorb in real time, but along the vertical axis here, we have how much of something there is in the Earth's crust. And along the bottom is how many atoms go into the, or what the atomic number of the material is. And what's important about the vertical axis is it's logarithmic, which means it's not linear. It's not like halfway up is half as much as the top. It's going up by factors of 10. And the green stuff, the stuff in the green bubble, if I make this work, stuff in the green bubble is really common stuff. So if we can make our energy storage device out of the stuff in the green bubble, then we're in good shape. If we try and spend all of our time working over here, where things are maybe 1/1,000,000th as prevalent as what's in the green bubble, we might make something work, but we'll never be able to scale it. And a lot of battery technologies are kind of using materials from this area. So this is very important, and part of the unmasking the pretenders is about finding out what we can use to make our technology. And this is that Donald Sadoway's starting point, and it's actually quite a good one. So in fact, we'll stick with him for a minute. I'm not a chemist, but his idea, which I think is quite a good one, is he's just going to make a bidirectional aluminium smelter, except he's not smelting aluminium, he's smelting magnesium. And he's actually had the benefit of that graph and choosing materials that are fairly abundant. And maybe he'll do very well. He's started a company. So my job is to think of doing it a different way, because I think we need a lot of contenders in this field. But before we leave batteries, we're going to just look at this graph. And again, it's a little bit difficult because the vertical axis is called EROEI, which kind of sounds like the punchline in Old MacDonald Had a Farm. It means energy returned on energy invested, which is just like embodied energy, really. It's almost the same idea. And a big number is good, and a small number is bad. And the thing that we used as a reference a minute ago is pumped hydro storage. So if something's not very good compared to pumped hydro storage, we're not going to use it. And here's virtually all of the different battery technologies that people have been thinking about. And you see there, the best ones about a 20th as good as pumped storage. And what that tells me is we're not going to make this out of batteries. Batteries may be very good for things like mobile equipment and computers, but I don't think they're going to do grid level storage. So we come back to the family tree. We've had a bit of an execution here. We've removed some of the demand related stuff. We're going to do the demand related stuff anyway. It's good. It's what's going to happen as we apply intelligence to the electric grid. So that's why some of it's missing. The other thing we've done is we've made things in sort of the blocks are the kind of to do with the scale that we could possibly do this at, in terms of the scale of the units that we might make and the scale of the power that or power levels that it might address. And you'll see there's only really 4 big ones left. So I propose to use the rest of the lecture really to just touch on those 4 and see where those might take us. The rest are now going to be retired to the bench. And that includes all the batteries and flywheels and other things that are either too consumptive of very expensive materials or which are not going to be big enough to eclipse demand management. Because if demand management is free, how could these things actually be developed? So just touch on gravity. Pumped hydro is essentially gravity storage, but we could actually make a big lump of something made of the Earth's crust and then raise it up and down. Lots of people are proposing this in different forms at the moment, and it's possible this could be a really clever thing to do, but there's a lot of practical problems in making it work, and I'm not sure that anybody's anywhere close to solving them, and so far it's only little companies with no resource working on it, so I wouldn't hold your breath. Another form of gravity storage is actually to invert the problem and think out of the box. Instead of bringing water and putting it up a hill, why don't we bring air and put it under the water? And that's being done in Canada, just outside Toronto in Lake Ontario. They're putting these bags under Lake Ontario and filling them with air. Now, if the air is at the surface or just under the surface, well, we're just sort of displacing the water uphill. But if we put the bags on the seabed, then in fact, by the time we get the air down there, it's compressed. And now we're starting this journey into compressed air, which will be a theme that we're going to continue. Because you can also store energy as compressed air. And in fact, at Artemis, we were approached quite a long time ago now, maybe about 5-6 years ago, by a company called General Compression. And they really got my attention because they said, well, we could store absolutely massive amounts of energy in massive caverns under the ground, and this is how we would make them. And I love the story about making the caverns so much, I'm going to tell it to you. So basically, you get a drill like you would drill for oil, and you drill down from the surface downwards, and you maybe go down thousands of meters until you find a salt dome. It's a sort of formation of natural salt. And you pump water, fresh water, down that hole, and it combines with the salt and makes a brine, and then the brine comes up to the outside of the hole, and you just keep that turned on until basically you make this cavern. And it costs you about $1 million to make the hole, but every additional cubic meter of cavern is almost free because you just have to leave the garden hose running. So it's a fantastic thing, and I saw that and thought, that's absolutely wonderful. There's got to be something in that. And so we actually, at Artemis, had some involvement with General Compression some years back, and I'll come back to that presently. But before I leave this slide, I just want you to notice something. You notice the lovely lawn-type green stuff on the top, and just an industrial shed which has the compressor and expander machinery inside the shed. So it's not very invasive. Everything's happening underground. It's wonderful. I was convinced. But to make something work in a salt cavern, you have a slight problem. You've got to make sure that the air gets into the cavern at roughly ambient temperature, because if you heat up the inside of the salt cavern, it starts to disintegrate. So the cavern usually has a cavern policeman who's watching the temperature of the gas going in to make sure that you're not doing damage to it. And if we compress air and keep it at the same temperature, we call it isothermal compression. So I'm afraid this is the part where I'm making you eat your vegetables. In fact, you're going to eat your vegetables 3 times, so get used to it. Something fading out about this laser. There we go. I'm also introducing you to an equation, but you won't have to get too excited about it. It's almost the same equation every time. So this is called isothermal compression, and basically I take a volume of air and I halve its volume, and its pressure goes up to double. And that's quite simple, and you can sort of imagine doing that with a sort of squashy thing. And interestingly enough, the temperature remains absolutely constant through that process. And you think, oh, that's interesting. But what that's not showing you is the fact that there's a huge amount of heat that's actually leaking out during that process and going out to the environment. But heat doesn't really flow unless there's a temperature difference. So that is a bit of a problem. And when General Compression actually made their facility, this is a pilot facility in Gaines, Texas. I went out there. Gaines, by the way, is, apologies to some of the Americans in the audience, it's a pretty desolate place. In any case, there was this pilot plant. You'll notice that the shed is quite small. That was because it was just a 2 megawatt installation. But I was a bit surprised when I got there, because instead of seeing that wonderful green lawn, I saw this sort of tatty thing here, which I'm calling the swimming pool. And they had basically, in order to absorb the heat, they had this massive volume of water. And the trouble with isothermal compression is that you're saying everything's going to happen at the same temperature, but I've got to store all that energy that's coming out, and it's most of the energy that's coming out of that process in the water, but I've got to store that energy without the water changing much in temperature. So I've got to have a vast amount of water. So I bought an energy storage cavern and machinery, and I got a free swimming pool. That's what they did. My interest started to wane after that point in compressed air storage. So we'll leave that one aside, and we're going to move up to the top corner here now, because this is really an interesting place. Isotropic compression. So if we're putting a lot of the energy that we're storing into heat, if we're using compressed air, maybe we should just forget about putting it into the cavern altogether. And to do that, we use a different kind of compression. Both of these, by the way, are completely reversible processes, and for this to work with any kind of efficiency, we have to use processes that are entirely reversible. So with isotropic compression, it sounds the same. We start with the same situation, but now we're going to compress the air, but we've got the air cavity or the container completely insulated. So the heat is no longer able to leak out. It stays in the container, and as a result, the air, as it's being compressed, gets much, much hotter, goes to a much higher temperature. And the other thing that happens is, even when we get to the same pressures we got to last time, we haven't quite reached the same volume. So this is a bigger storage volume required. If we look at the equation that we talked about earlier, PV now has a little exponent, and that exponent comes in 2 flavors. So if you've got a gas that's like air, the gas molecules have 2 atoms, and gamma is always 1.4 pretty much. If you have a noble gas like argon, gamma can be 1.67, and that means that when you compress it, it gets hotter, which is quite useful if you're doing energy storage. Now, this sounds like a fairly academic exercise, except that somebody said, wouldn't that be a good way of storing energy? And this company named themselves appropriately Isotropic Limited, and they built this piece of kit, or at least I think they built some aspects of this kit. And this is important enough that I'm going to have to take you through how this works. I think it's incredibly elegant, and the engineers amongst us, I think, should appreciate that. So basically, I have 2 containers, this very big container here, and a smaller one on this side. The blue one is sitting at atmospheric pressure, so it doesn't have to be pressurized. The red one is sitting at 12 bar. between the two containers I have this machinery, and basically that's an electric machine that's taking electricity from the grid and making the machine go around. And the machine itself has got a lot of the components of a car engine in it. It's got a piston-related, or piston compressor and a piston expander. And basically there's a loop of plumbing that joins the two containers, and I'll explain how that all works. The blue and red bits, by the way, are gravel. So it's a very low-cost way of storing energy by heating something up and cooling it down. And the way that works, let's start at the top. Start here. We're starting with argon, which we mentioned a minute ago why we might want to use argon. Argon is sucked into the compressor, compressed up to 12 bar. When it's compressed, it gets hot. We talked about hot a minute ago. And the hot gas at 12 bar comes into this pressurized container and starts percolating through this gravel. And it makes the gravel, where the gravel isn't at 500 degrees yet, it absorbs the heat from the argon and cools the argon down. So that we see at the bottom, where the gravel is still sort of vaguely warm, that's where it's accepting heat from the argon as it passes through. And by the time the gravel has taken all the energy out of the argon gas, it comes to the bottom. It's still at 12 bar, but it's now at ambient temperature. Now we take that ambient temperature out of the bottom of this container and into an expander. And everybody's got one of these at home. It's called a refrigerator. When you want to cool a gas, you expand it. That's what happens in your refrigerator. And so we expand gas from 12 bar and ambient temperature, and guess what? It gets really cold. It goes down to minus 150 C. And we use that cool, which is kind of the inverse of heat, and we're now going to cool down this second container, which is also full of gravel. So now the cold air, or the cold argon, is going to pass up through the second bed and cool the gravel down, and finally it will warm up and get back to the starting condition of atmospheric pressure and ambient temperature. So that was their brilliant idea, and when I saw that, I thought, that is absolutely fantastic. How did they think of that? Generally, for us engineers, we're taught that going backwards from work to heat is a very bad move, because we have this thing called Carnot efficiency, and Carnot is a hard taskmaster, and he says, no, mechanical and electrical energy is far more valuable than heat. But Carnot is working in two directions here, so it actually, what you're really trying to do is avoid irreversible processes, and that's what they've sought to do. But the other thing that they've done, and I think a really important thing, is they've gone back to Sadoway's first principle. This is Sadoway's slide, by the way. To make it dirt cheap, make it out of dirt, preferably local dirt. I would say that gravel is dirt, so that is something that maybe could move forward. So, how do I enter the picture? Well, you had an introduction, a very kind introduction from Leslie about Artemis. We were working with general compression just about the time that Mitsubishi bought us. And up to that point, we had only made relatively small machines. We made a small proof of concept machine with general compression. We allowed them to drive their expander, compressor expander. They were very happy with what we'd done. It was the future for them. Unfortunately, Mitsubishi took us away from them when they bought us and said, you people have got to work on wind. So we couldn't really keep working with general compression. Didn't mean we'd stopped thinking about energy storage, but it did mean that our practical working on energy storage had been sort of stalled out. Now, you also heard that I turned up in 1978, and I worked with Stephen on the duck transmission. Stephen identified quite early on that in wave power you start out with waves that are very high forces, very low speeds, very irregular motions, and you've got to get from that to a shaft that's going round to generate electricity at 50 or 60 hertz. And that machine that you have to put between the waves and the electrical generator is called a transmission. And first of all, he looked at how to do that, and he puzzled away, and eventually he said, well, we've got to do it with hydraulics. And then he looked at all the hydraulics catalogs, and he said, well, unfortunately, these aren't going to work for three reasons. You can't buy hydraulics that are big enough, because he wanted to work in the megawatt scale, and so do we. you can't buy hydraulics that are controllable enough, and to some degree that's been addressed, but all hydraulics are just too inefficient. And we could pay a huge amount more for a little bit more efficiency. So we formed a group within the wave power team, and we started developing hydraulics, and we came up with digital displacement hydraulics. And Stephen also was a co-founder of Artemis, I should say. And after several years of working on it within the university, we moved it into a company. The company was actually on site here for the first 13 years of our life. University ran out of space, and we ran out of space, so we then moved down to Lone Head. Simon, who's sitting there, actually helped us find a place, which was very good. And we're still down there in a much, much bigger facility. And during that time, we built machines, first of all, little ones that we could afford to make, and after Mitsubishi bought us, very, very big ones that are of a scale that could start being meaningful in grid electrical storage. So that's this wonderful gift that Artemis and Mitsubishi have given me in my search for a grid-scale energy storage. This is a pump motor that can controllably move oil down a pipe at pressure. So we can convert a rotating shaft, to oil moving down a pipe in a very efficient and controllable way. And that is absolutely pivotal to the concept I'm going to put forward. The other thing that happened was we built this team. We started out with 2 people, and by the time we were finished, we were about 50 people, and 4 and a bit years ago, we were bought by Mitsubishi, and then I began laying in my succession plan, and a year and a half ago, almost 2 years now, one of my very capable people that was part of the fantastic team, many of whom are here in the audience tonight, Neil Caldwell took over from me as managing director, which meant I could do other things. And very, very happily, about 8 months ago, I was asked if I would join the university as a professor. So here I am as professor of energy storage with this incredible dowry of interesting machinery that I can apply to make effective energy storage. But I should say that during the history of Artemis, this was not the first time. The general compression thing was not the first time we met energy storage. We actually had thought about it a lot earlier because we knew that with wave energy, which is quite variable, we need some form of buffering, came up with the idea of pumping oil into big steel tubes. And this was a diagram that I had prepared in 1996, so 19 years ago. And I went to various VCs and tried to sell them on this, and it was a complete flop. Because basically I knew quite quickly that I was operating in the wrong area. Nobody needed short-term storage for the grid. They needed days of storage rather than hours or minutes. And also the storage in this case was essentially the steel tubes that we were pumping oil into, and the embodied energy in the steel was just way too high. So from the vantage point we have now, okay, this was going to be, round-trip efficiency-wise, this would have been somewhat better than pumped hydro, but in terms of the embodied energy, not even on the starting grid. Anyway, we left that behind, moved Artemis forward on various fronts, and much, much later, here I am now trying to put all these different components together. So coming back to isentropic and their wonderful thing, I looked at that and I thought, well, actually there's 2 problems with this thing that I don't really like. The first problem was that, we'll start on the right-hand side, this containment here is at atmospheric pressure. So this whole argon pumping loop that's here is all is working with a very low pressure on one side and not a very high pressure on the other. And that means that the swept volume or the sizes of the pistons and cylinders got to be absolutely immense to move any power at all, because it's sucking air in, or argon in at atmospheric pressure. It's got to be absolutely steam engine size to get anywhere. Now, I didn't like that. And the second thing I really didn't like was that the high temperature containment, which is on this side, is sitting there at 12 bar. So you've got this nice cheap gravel, but it's surrounded by this incredibly expensive high pressure vessel. And that's a lot of embodied energy in that vessel. So I sort of thought, well, could I take this principle of storing energy in heat, and could I use the compressor and expansion technology that we first viewed when we were working, or first came up with when we were working with general compression? And my starting point was actually something that it started as kind of hands-on exercise across the road here. We had a compressor in our workshop. It was like this one. It's called a hydrovane. And I'm not going to teach you how to fix one while you're sitting there, but it's maybe useful to show you how it works. So the sort of gray area is where the air part is moving, and the black thing in the middle is the rotor, and it's going round and it's trapping air between the vanes. And as it rotates, it's actually compressing the air, and the volumes between the vanes are getting smaller and smaller as it gets towards the top. And the air comes out compressed. That's obvious. What's not obvious is there's actually a completely secondary thing happening there, and it's all in the red. And that's oil. So basically what they were doing, and I sort of encountered this, what are these nozzles? There's nozzles right there, and they were spraying oil into the compressor. Why were they spraying oil there? Well, I thought initially, well, they're for lubricating the thing, to keep the friction down. Then I thought, well, actually, maybe this oil is quite useful in order to reduce the leakage, because it's harder for the air to leak around the vanes if the oil is in the way, because oil is quite viscous. And then I realized that it had a really, really important function, and that function is that if I take air which has got very little mass and I compress it isotropically like it, it'll get very hot. But if I could spray oil into that air and change the properties of the fluid, then it wouldn't get so hot. The air would come out much cooler, and actually I could make the whole thing run more efficiently. And that's what they're doing. It's been done for a long time. This thing's been, you could buy this thing for more than almost 100 years. But basically the oil comes out, goes through a cooler, and then gets sprayed into the inlet where it's mixing with the air. So we've got an interesting opportunity here to kind of make a tailored fluid by mixing gas and liquid. And if you have a material like this, we could call it a polytropic fluid, and we can give it a process called polytropic compression, which is almost the same as what we had before, but we're going to just change one little thing, and that exponent gamma that we had before, which was locked into being 1.4 or 1.67, is now completely our choice, because we can choose how much liquid to mix with the gas, and that liquid is kind of adding thermal mass to the gas, so that as it compresses, some or maybe even most of the heat is going into the liquid. And that's what the compressor, that hydrovane compressor, is doing. So that was my concept. I'm not going to dwell on this in any great depth, but the concept is very similar to the isentropic one, in that we have a hot store and a cold store, and we have Artemis pump motors, and they're driving these long sort of steam engine-like things, which are expanders and compressors, and they're compressing air and expanding, or at least compressing and expanding argon. And it's doing it in a very controlled fashion with very high efficiency, because that's a property of the Artemis machines. But then we've got a whole bunch of extra plumbing in here, and that's the equivalent of the oil. We're mixing liquid into the compressor to take most of that heat into the liquid. Most of the heat of compression is going into the liquid, and then we can take it out of the pressurized environment, and we can dribble it over the gravel, and the gravel can be outside the pressurized environment. And that means we've got rid of one of the big problems that isentropic have. We no longer need a big pressurized containment. The other thing we can do is we do it on the low pressure side, and then the argon loop that's happening just in this space here is actually working from whatever pressure we want at the bottom. So we can maybe run from 20 bar up to 350 bar, or 20 atmospheres to 350 atmospheres. And that means that the gas is always very dense, and we don't have to have things the size of ship engines in order to get any power capability. So that was the starting point. And I did some sums on the back of an envelope, and then I wrote an application for the EPSRC and Innovate UK and submitted it, and they came back with the green light about January time, and we've managed to get the first phase of our Catalyst program on the go to do this now. So when somebody asked me what was I going to do about it, that's what I'm doing about it. We're actually working on this, and I've got a very capable young PhD student who's sitting there, Dan, who actually helped me put a lot of the slides together, for which I'm very thankful. And I've just been joined by Rick Jeffries, who's one of my old pals from his days in ConocoPhillips, where he also worked on the general compression project, more on the cavern side. And so the three of us have made a little team, and we are, over the next year, going to try and explore whether we can be in contention and beat Donald Sadoway out of the ring with his liquid metal battery. So that's what we're going to do. The vision, by the way, is that at the end of this, we make something like, a bit like a McDonald's restaurant. So that's something that a team of people can turn up and build in 3 days and have more or less operational. It'll be the same everywhere. And that the capacity of that device or that installation would be enough to satisfy the storage requirements of a conurbation. So you can imagine buying 2 acres in Pennycook and building a big unit like this, digging 2 pits, putting in your gravel, your local dirt, as it were, and suddenly having this capacity to average out the solar energy, which will be largely generated around the conurbations. That's the vision. Right. Now comes the philosophical message. I'm just about finished, so I hope to not keep you too much longer. When I joined the university in 1978, after these 2 oil shocks, we kind of knew that we had to do something about fossil fuels. And I think the great crime of my generation is that we didn't do what we needed to do. And of course, we were sitting in the West in this relatively comfortable and affluent lifestyle, and all the people in developing countries saw us and thought, wouldn't it be nice if we could live like that too? And we should have been thinking, well, actually, if they want to live like that too, like us, then we should be developing and putting some of our resources towards developing the technologies that we need to make our life sustainable. And of course, those people are now a lot more than there used to be. I think I saw the population of the Earth is still accelerating madly. And we haven't actually developed those technologies. And that's really put us in a rather dangerous position. And this is the last piece of homework. This was suggested by my friend Richard, who's somewhere in the back. He put us onto reading this book not long ago. And this woman, Naomi Klein, who's a Canadian writer, has written this book about how the climate is really on a disaster course. We're really on a sort of super tanker that needs to turn around, and we're going to have a very hard time turning it around quickly enough. Her solution to this problem, I think, is a bit of in the fantasy land, but it's certainly, the problem is real enough. We've got to do something to turn our energy profligacy off and start doing stuff that it's responsible. Now, it would be easy to think that it was impossible, and it would be easy to end this on a very downbeat note, but I think there's actually something that we can look at and be quite amazed by. So we go back to that same time frame as the beginning of my career, and we get this funny-looking turbine. And I actually came to this by accident in 1978. I saw a man climbing out of it with 2 oily spanners. And what I didn't realize at that time, and until fairly recently, it was actually the biggest wind turbine in Europe in 1977, 30 kilowatts. 2 months ago, some of our Artemis directors and myself went across to Hunterston, where we celebrated the launch of this wind turbine, which is not the only wind turbine that's working at 7 megawatts, but that's more than 200 times greater than that turbine of 37 years ago. And this is a technology that emerged without much support. There's no military backing for it. There was no secret connivance of CIA. This was done entirely by enthusiasts and competent people, some of whom were effectively amateurs. And yet they managed to turn something from an idea into something that's now being quite accepted as a serious form of generation. In fact, there were times in the last months when more of Scotland's electricity came from wind than anything else. But again, we have the averaging problem. Right. I think I've done my nut. I think I'm going to stop. And I've been told that there's going to be drinks outside and nibbles. So I would invite all of you to come out aside and share in those with me, although I think somebody said there might be questions and answers. Is that the case, Leslie?
Well, I think let's all thank you.